Hi everyone, it's lovely to meet you. If I haven't met you already, I look forward to meeting you over the next couple of days. Before I start, I want to pick up on something that Mikhail said in his introduction, which I personally found interesting because it does relate to the topic that I'm going to talk about today, which is these systems which are referred to as neuromorphic systems. Now, this research area actually stemmed out of engineering and specifically electrical engineering. And I tell you, what I'm going to talk about in the context of neuromorphic engineering is unconventional to them. They really do not like the idea of disorganized systems, systems that are complex, that exhibit dynamics that are unpredictable. And so your comment there, Mikhail, really does hone in on this idea of, a little bit of antagonism between the design type of approach versus, the undesigned approach, if you like. Thank you very much to Mikhail, Mike from the University of Sydney, and no doubt other people at the University of Sydney who helped to organise this. And of course, the Auckland team, I look forward to meeting you. And I also want to acknowledge all the people who have contributed to the research that I'm going to be presenting today. Most of all, PhD students, as we all know, they're at the cold face of most of the work that many of us do. So my outline of the talk today, I'm going to give you a little bit of motivation and rationale for the topic of my talk. And the topic of my talk is specifically on these really interesting physical devices known as neuromorphic nanowire networks. So neuromorphic means brain-like. Nanowires means they involve nanotechnology. So I'm going to tell you a little bit about that aspect of it. And networks means, yes, of course, they involve networks. I'm going to talk about the dynamics that emerges from these systems. And then I'm going to talk about some really interesting applications to information processing. I always struggle with whether to describe this as information processing versus computing. I don't actually think computing really fully describes what these systems do, and I'll try and explain that as I go along. And then I'm going to summarize the key results and also draw a conclusion from what I've seen so far. This is ongoing research, so if I come back in 2 years' time, maybe I'll conclude something completely different. We'll see. So first of all, a bit about the motivation and rationale behind this research for me. I'm a physicist, I'm not an engineer, so I'm not approaching this from the traditional neuromorphic engineering approach. So I'm really motivated by the idea of the physical nature of intelligence, if there's such a thing, exploring that idea. And of course, the intelligence itself, it still doesn't have a proper definition. If you ask different people, they'll give you different answers. And of course, if you ask someone from the artificial intelligence community, they'll say, oh, we already know what it is. We can produce it. But there's so many interesting systems that exhibit seemingly intelligent behaviors. And we've seen a lot of these intelligent behaviors, and Mikhail has actually provided a few examples of this in his opening slides. We've seen a few of these interesting behaviours in non-biological systems. But of course, the paradigmatic biological system that exhibits intelligence that we know about is the human brain. And of course, other animals exhibit varying levels of intelligence as well. So two questions that really motivate me and which are the rationale behind the talk today, at least, is the first one being, can we emulate brain-like intelligence in inorganic, so non-biological physical substrates? And the second question is, well, if we can, and I'll show you, yes, we can, what's the physical nature of that intelligence? So maybe another way to look at this is to think about the human brain, think about all the neurons and the neural network we have in the brain. If you stripped out all the biological processes, reproducing cells, the immune system and so on, if you stripped out all the messy biology, what would you be left with? Is that the physical substrate of intelligence? So just to kind of motivate this a little bit more, I do want to draw some comparisons between artificial neural networks and biological neural networks. So probably most of you know a little bit about artificial neural networks because it seems the whole world is infatuated by artificial intelligence right now. But just for me, I've jotted down a few things that I can draw comparisons against biological networks. So on the left-hand side, artificial neural networks are intrinsically static structures. You train the weights into some fixed state for a particular learning task. And then you apply that trained neural network to perform that task, to perform inference, as they call it, over and over again. And then you need to update those weights when you have new information, new data. And it's well known that artificial neural networks, at least these sort of multi-layer type of artificial neural networks, are what are known as universal function approximators. So as long as you have enough resources, you have enough neurons, you can pretty much approximate any function. And what they're really, really good at is finding stationary patterns in really big data. And I think, you know, in many cases, they can demonstrate superhuman performance. In contrast, biological neural networks are intrinsically dynamical and they have recurrent connections. And that turns out to be quite important because recurrent connections introduce delay lines. So you have delays in the dynamics. As a result of that, they end up demonstrating to be universal ODE approximators as opposed to universal function approximators. They excel at adaptively processing information from data that is noisy, sparse, dynamic, and so forth. So quite contrasting against artificial neural networks. And so the types of learning that we can describe for artificial neural networks is statistical learning, whereas for biological neural networks, it's physical learning. So let me explain what I mean by physical learning a bit, or at least my argument for physical learning. We already have examples of networks that are made out of different physical substrates. On the left-hand side here is an electrical circuit network made of variable resistors, so resistors that have varying resistance values. And on the right-hand side, we also have other examples of similar networks made of physical substrates, mechanical and optoelectronic networks in this particular cases. So physical learning is a type of learning that exploits the physical properties of some substrate. In these examples, these are electrical circuits, and I'm going to actually present another example of electrical circuit, but slightly different there. But there could be other examples of physical substrates that exploit other physical properties. So we could just have purely optical systems. We could have magnetic systems, for example. So thinking about different physical substrates that have different physical properties that produce dynamical responses to inputs that can then be used for some computational or information processing tasks, depending on how you want to look at that. The reason why I don't like saying computation is because it always conjures up the idea of logic gates. And I really want to move past that. This is not what we're talking about necessarily. It's not necessarily digital electronics. It might be, but it's not limited to that. So let me introduce now these interesting physical systems known as neuromorphic nanowire networks. So, as the name suggests, these are physical systems, and I'll call them substrates because we're going to use them as substrates, comprised of nanowires. Now, nanowires, the nanobit means that at least one dimension of that object has to be on the nanoscale, typically less than 100 nanometers, or all 3D dimensions could be. In this case, it is one dimension, so the cross-section is typically about 4 or 5 nanometers across. Their lengths can be anywhere from about 50 microns to a few hundred microns, depending on how they're synthesized. They're very easy to synthesize in the chemistry lab. I don't do that myself, I'm not a chemist, but I'm told they're very easy to make. And in fact, a couple of my physics PhD students have made them in the lab, and you can make them in a couple of hours, so I'm told. So they're kind of long and stringy when they're synthesized, and they kind of form this very disordered structure naturally through this process of self-assembly. And I'll show you in a moment why you can also describe them as self-organized or guided self-organized systems. So on the top right-hand side here, you can see a scanning electron microscope image of one sample of a nanowire network. And you can see straight away that they're very heterogeneous. This is not a homogeneous random network. It actually exhibits some really interesting network structures. And this just forms naturally through self-assembly, just like complex biological molecules form through the same process. Bottom-up synthesis, bottom-up self-assembly. This is quite different. So in nanotechnology, there are two ways to fabricate nanoscale systems and devices. One is through the top-down design-driven technique. And again, this is going back to the sort of engineering concepts, where basically you design something like a chip, for example. That's a classic example. And you design that right down to the smallest nanometer, and then you go to your clean room facilities and you use nanofabrication facilities like electron beam lithography and all that sort of thing to make sure that you're able to design down to that last nanometer. In contrast, the other 50% of nanotechnology is done in the chemistry lab. You don't need clean rooms. You just mix things up and you let them form some really interesting structures. You control the formation of those structures through temperature and pressure. There are a few other factors that take into account. So that's what we're talking about here. Okay, so first of all, just visually, qualitatively, you can see that the structure of the network that's formed from these nanowires is at least qualitatively similar to biological neural networks. And I would argue that that is because of this self-assembly process. And in fact, we've looked at this quantitatively. We've actually developed a model of these nanowire networks, and I'll go into details about the model in a moment, to simulate them and to simulate a whole range of different structures. Separately to that, then we look at the structure-function relationship with these nanowire networks. So just in terms of the structure, however, we've actually shown that nanowire networks exhibit small world topology. They also exhibit interesting connectivity features like hubs, for example. And the interesting thing about this study that was carried out by one of my PhD students, Alan Mokler, is that he actually used all the network neuroscience tools that have been developed specifically for doing, brain network studies. So we've just borrowed all those tools and applied them to this interesting physical substrate system to determine the quantitative aspects of the network topology. So nanowire networks are electrical systems because they exhibit really interesting responses to electrical stimulation. And the responses that are observed are quite interesting in the sense that they're highly nonlinear. So what's been observed is that when you apply a bias across a nanowire network, for example, nothing happens for some time. There's a sort of a very low level of current that flows through the network. And then after a while, bang, it just kind of, you get this huge jump in the network conductivity and the current flow through the network. The reason for that is because throughout the network, everywhere that the nanowires overlap, and you can get one single nanowire if it's particularly long, you can have multiple cross-point junctions. Everywhere that the nanowires overlap, it acts like an electrical junction. And in particular, with the nanowires that we've been working with, they're made of silver. So there's a silver metal, and it's coated with a very thin 1 to 2 nanometer layer of insulating polymer material. So where the nanowires overlap, you get a insulated metal junction. And so if you imagine an electrical bias across that junction, nothing happens for a while, but if you can zoom in on an individual junction, you actually see switching behavior. And that switching behavior is due to the following process. So this diagram down here in the middle part, for those of you on Zoom, I'm pointing sort of on the bottom middle part of my slide, looking at the low conductivity off state versus the high conductivity on state. And what happens is that across that metal insulator metal junction, once there's a bias across there, you get individual silver cations migrating across. And on the other side, there's a redox reaction that then neutralizes those cations. And so then you end up forming a neutral atomic conducting bridge. These are silver metal atoms. So they'll now start conducting. And so current can now flow from one junction to the other. That junction was only a few nanometers thick. So in addition to that, that kind of ionic current flow, there's also electron tunneling that takes place before that bridge actually connects to the other side. So there's two interesting bits of physics there that are contributing to the switching, electrical switching behavior across that junction. So the switching is kind of like a transistor, but it operates on a different physical process. And of course, the other difference is that unlike transistor chips, we don't have regularly arranged or regularly placed transistors on the chip. We kind of have this highly disordered, self-organized arrangement of these electrical switches throughout the network. Now, the other interesting thing is that these electrical switches, these nanowire junctions around the network, kind of behave in a similar fashion to synapses between neurons. And synapses between neurons are known to operate on two bases. That ultimately, they're triggered by electrical signals that then get converted into these chemical signals. So the chemical signals are enabled by these neurotransmitter molecules that propagate from one neuron to the other. And so that's what's responsible for transmitting signals or transmitting information between neurons. And of course, there's a whole bunch of neurons in a biological neural network. So in a similar fashion, we have quite a complex network. We often refer to our switching nanowire networks as these junctions as synthetic synapses because they operate on a similar principle. Now, in terms of doing electrical measurements on these systems, so I mentioned that once these electrical junctions feel a bias across them, they'll eventually switch. But of course, we don't actually directly implement an electrical bias on each and every junction. We just have an input somewhere in the network, and we make sure there's a drain somewhere else in the network. And we let the network evolve in its response to that electrical bias that's placed across the entire network. And so what that means is that when you apply that voltage bias across the network, the voltage is redistributed across all the junctions in the network. And that voltage redistribution is continuously evolving. It's dynamic. So every single junction in the network is continuously changing its bias in response to the current internal state of that junction, as well as its connectivity to its neighbours. That's why that connectivity is so important, because it provides a feedback on the dynamics, on the internal states of each and every junction. On the bottom right-hand side, there's a phase plot in current voltage space. And these are kind of sort of standard electrical characterization measurements that you would normally apply to similar systems to these, which are called memristors, but they're not in a network. They're just kind of individual devices that are often made in the lab. But they exhibit this characteristic hysteresis curve. So when you increase the voltage, and this is for an AC signal, you increase the voltage, not much happens in terms of the current flow. And then after some time or above a threshold voltage, the current suddenly jumps and it goes up to some maximum, and then it comes back down, passes through zero. And then when you go to a negative bias with an AC signal, it goes down to the other side. So 2 points here. One is that clearly there's hysteresis there. And the second point is that this is for multiple cycles, and you can see slight deviations from cycle to cycle, but it kind of it's kind of like a, almost like an attractor state in this phase space. And I'm going to come back to that point a little bit later on. So I mentioned that we've actually developed a model for these memristor networks. Valentino, who I've noticed here in the audience, is going to tell us a little bit more about some of the modelling that she's been doing on memristor networks as well. So that's going to be later on this morning. But in our specific model for these specific systems, we've actually had to model this sort of threshold-driven bipolar switching phenomenon, which is highly nonlinear, and in addition, as I mentioned, in addition to that ionic current due to the formation and also the decay of that little filament, the nanofilament that forms across the junction, we also have electron tunneling that kicks in as well. So that adds an extra degree of nonlinearity in there. And one of the other important aspects of the model we've developed is that because this is an electrical system and we've got a network of all these electrical switching junctions, we actually have to ensure that at each and every time point, Kirchhoff's laws are satisfied. So Kirchhoff's laws are laws that define the conservation of electrical energy and electrical charge. And that's really interesting too, because it provides this physical constraint on the network dynamics, that constraint at every single time point that we have to conserve the energy and the electrical charge there. And so again, you know, the idea that there's very few free parameters. Of course, in our model, we have some free parameters, but that physical constraint actually plays a really important role in the evolution of the dynamics of the network as a whole. Okay, so now I'm going to look, now I'm going to present a little bit more about the dynamics from these systems. And specifically the brain-like dynamics from these systems. So I'm going to talk about 4 specific effects that we've observed in these systems, and we've observed it both experimentally and in simulation as well. So I'll present a mix of results from those 2 things. So first of all, on the right-hand side is just a little animation showing a modelled nanowire network, memristic nanowire networks, under an AC bias. So on the bottom right-hand side, you can kind of see a little triangular pulse down there. And in the network, you can see how the conductance path evolves from the source point, which is the top red point up there. And then there's a sink where the current leaves the network down on the bottom right-hand side. So just to give you an idea of what these simulations look like. Okay, so one of the first phenomena we've seen is a first order phase transition, a discontinuous phase transition. And how we've been able to observe this is by applying a constant DC bias across the network for a period of time. And then we can measure or simulate, these results here are simulation results. We can measure the network conductance as a function of time. So this is like the conductance time series, if you like. And the curves shown here on the left-hand side are different conductance time series curves from the network for different input voltages. And again, just to remind everyone here that, you know, that the idea of guided self-organization in this context means we're actually inputting this voltage. So the voltage source is what's guiding the network response in this sense, in this context. So for different voltage inputs, we can kind of see a characteristic behavior where the network conductance jumps by, in this case, 3 orders of magnitude. Note there's a logarithmic scale on the vertical axis there. And that happens also above a threshold voltage. So you can see a difference between a couple of those curves there. And when we go in and have a look at the steady state network conductance, as a function of the input voltage, we actually see a discontinuity in that relationship. So we've been able to identify this as a first order phase transition. And interestingly as well, for we've been able to also identify the conditions under which that first order phase transitions to a second order continuous phase transition. And that happens when, for an individual junction, the difference between the on and off states is less different, if you like. So on the right-hand side, oops, I thought that was a movie, but it looks like it's not. So on the right-hand side, this is just showing a visual of what's happening in the network for each of those three different curves for different voltage values. The next phenomenon that I'll describe is a phenomenon known as switch synchronization. So we're in this example, it's the same setup as before. So we just apply a constant DC bias across the network. These are simulation results because we can't actually observe what's going on at the individual junction level experimentally. So this is part of the reason why it's useful to have the model that we developed. So on the right-hand side, this is a similar plot to the one shown previously here, but for just one of those curves. And for one of those curves, that the total network conductance is shown in the dashed red curve here. And all the curves underneath the dashed red curve, which shows the total network conductance, are individual conductance curves for the individual junctions along that path between the source and the sink. So this is the first conductance path that forms. At later times, you'll get branching off that main conductance path. But for this as soon as this conductance path forms, we can actually go into the simulations and model the evolution of each one of those junctions on the main conductance path. And you can see that some of them form straight away. And in fact, what happens is that the ones near the source and the drain form fastest, and then it kind of moves in together and then it connects that way. So some of them form early on, and then some of them form later on. And then as soon as the last one forms, that's when the network conductance jumps into this higher state. So in that sense, the network conductance switches in a synchronized way while these other junctions wait for the later ones to switch on. The third dynamical properties, neuromorphic dynamical properties we've observed here, and I'll say this because all of these dynamics have been observed in one form or another, also with neuroscience studies. So the third dynamics we've observed is order to chaos attractive dynamics. So I mentioned briefly before that under an AC bias, under multiple cycles of an AC bias, you'll see those trajectories start to diverge a little bit, but they don't actually, completely diverge throughout phase space. They don't occupy all of phase space, so it doesn't turn out to be full-blown chaotic dynamics. But these are three diagrams of that IV response curve under an AC bias for different values of the Lyapunov exponent. So the top left-hand side is lambda less than 0. The top right-hand side, figure B, is for lambda approximately 0. And the bottom one is for lambda greater than 0. And you can even see that for lambda greater than 0, the positive Lyapunov exponent, it doesn't actually give you full-blown chaos. So it's much more, it's kind of like bounded, if you like, in that sense. But you can see some differences in those IV trajectories in this phase space. And then the last dynamics that we've observed is particularly interesting. It's known as avalanche criticality. So probably most of you are familiar with criticality, but unless you work in the neuroscience space, you may be less familiar with the concept of avalanche criticality, which is really been something that's attracted a lot of attention in the neuroscience community. So in live neuronal cultures where neuroscientists do experiments, they do experiments in a similar way to the way in which we do experiments here. You stimulate the neuronal culture, and then you can also record the responses of the neurons. And you can only do that, you know, under some constraints, because you're limited by the number of electrodes you have to actually transmit those electrical signals and then record back again. But in any case, with these type of experiments, you can actually measure the spikes that neurons exhibit. And the spikes that neurons exhibit are the dramatic changes in conductance of the synapses between neurons. So again, drawing strong similarities to what we've observed in these memoristic nanowire networks. So the spikes, or action potentials, which is sort of more biological description of them, exhibit some really interesting statistics. And it's been shown by many studies with a lot of different neuronal culture experiments that you can actually see criticality under some condition. And it's described as avalanche criticality because the idea is that as soon as you start getting some spikes, some action potentials in the sample of neuronal tissue, that'll trigger other spikes in neighboring neurons as well. So again, it all comes down to the connectivity and how that information in terms of the spikes or the action potential is then subsequently transmitted throughout the neural network. So we did exactly the same study in our system because we also produced these dramatic changes in conductance as a result of the memoristic switching in our nanowire network. And we were able to show, in two different systems, in fact, avalanche criticality as well. And the hallmark of avalanche criticality is from the statistics of the spikes. You basically have to collect a whole bunch of spikes to do this kind of statistics. So I've got quite a lot of plots here, so bear with me while I explain what they are. First of all, on the top panel, AG PVP nanowire networks. This refers to the silver nanowires coated with a PVP insulator that I briefly mentioned before. So that's one particular nanowire network system. And we repeated this experiment. These are all experimental data. We repeated this experiment with a different type of nanowire network, a silver selenide nanowire network. So we have two different physical systems on which we did the same experiment on. Each one of these columns, well, actually the first two columns represent different probability distributions for the spike statistics. So the first column represents the probability distribution for the sizes of the spikes that are observed. So how many spikes there are in particular events. The second column, the one in the middle, represents the probability distribution for the time of the spikes, so the duration, if you like. And the third column represents the average size as a function of the duration. So it's kind of a combination of the first two. So there are very specific criteria for these probability distributions to meet the criteria for criticality. And of course, the first one is that they have to exhibit scale-free power law distributions, which they do for both the size and the duration. So we tick that. But there is another crucial criterion that needs to be met. And that's a criterion that relates the power law slope of each of those first two power laws to the slope of the third, the average size as a function of duration. And that's a very well-known relationship that depends on the university class of the particular statistics that you're measuring. So we were able to confirm that relationship for these nanowire network spike statistics, and therefore able to show avalanche criticality in these systems. And it's interesting to relate this back to studies that have been done on criticality in the brain, because criticality in physics, at least, is often understood with the most basic model, which is the Ising model. And in that context, you can identify an order parameter and a control parameter. In our case, for the nanowire networks, the control parameter is voltage. We're inputting the voltage into the system. And the order parameter is conductance. We've been measuring conductance, which is sort of like the system level network conductance that we can measure from the system, as opposed to in the Ising model where the control parameter is temperature, the order parameter is magnetization. But in any case, in this qualitative diagram that's been drawn for brain studies where avalanche criticality has been observed, the general idea is that for low control parameters, the idea is that the brain has these different regions which are generally uncoupled, they remain uncoupled. And so the activity of the brain is largely uncoordinated. And then if you go to the other end of the spectrum at very high control parameters, there's too much integration, saturated cortical activity. So in other words, the information kind of just spreads indiscriminately throughout the brain. So that's no good either. So somewhere in the middle, there's this kind of Goldilocks zone where you have this critical point for a critical control parameter value, where there's a balance between integration and so-called segregation. And that's kind of like being proposed as the optimal regime for cognitive function. Okay, so speaking of cognitive function, I'll just demonstrate some of the information processing tasks that we've been able to demonstrate. And we've been able to do these tasks using a particular framework known as reservoir computing. And the basic idea behind reservoir computing is that you have a physical system, usually a complex physical system, and ideally a network with recurrent network. And although reservoir computing was initially developed as a software type of approach to kind of get around the problem that other static neural networks face with dealing with dynamical input signals, there's an important difference between software-based reservoir computing and physical reservoir computing, where you're using a physical reservoir. And that is, at least in our case, our physical reservoir is an electrical physical reservoir. So we are constrained by those conservation laws. Now, the other important difference between our physical reservoir and software-based reservoir computing is that in software-based reservoir computing, you're basically choosing a mathematical activation function, some sigmoidal function like hyperbolic tan, I think is commonly used. In our case, we actually have physical model for what's happening between the nodes. We have this memristor process happening between the nodes. So that's our activation function. So those are the two key points of difference. We have physically motivated activation function that's enabling talking between the nodes. And we also have a physical constraint by the conservation laws. So it is quite different from standard reservoir computing. So I'm not going to spend too much going through all these tasks because I realize we are close to time, but maybe I'll just go through this one because maybe many of you are familiar with the Mackey glass signal. And of course, for some values of the time delay parameter, you can turn the Mackey glass signal into a chaotic signal, and you can choose the degree of chaos for that signal. Now, there's a well-known task, which is predicting the Mackey glass signal at some time steps ahead. And quite often, when you go and have a look at the different approaches that have been proposed for this prediction task, you'll find that it's often done with the time delay parameter value just as the signal becomes chaotic. And they say, oh, we've predicted a chaotic signal. But actually, the really difficult task is, okay, can you predict it when that time delay parameter is much higher, when the signal is really into a chaotic dynamical regime? So we've attempted that. and we've attempted it using a reservoir computing approach. But we've also, in doing that, we've also demonstrated something known as transfer learning. Transfer learning is when you learn something in some particular domain and you use that knowledge to learn faster in that same domain, but it's a slightly different task. So in this context, what we've done is we've used, and this is only in simulation, I might add, so we haven't tried this with a real physical network yet. So we've actually used a highly chaotic Mackey glass signal and attempted to do the prediction task on that, and then use the state of that network to actually do the prediction task on less chaotic Mackey glass signals. And we found that by doing that, we're actually able to achieve much higher performance than just doing the prediction task outright without, if you like, what's the word I'm looking for? Pre-training the network beforehand. And I want to say something about this task because this is a really interesting task as well. In this task, we input a 1 Hertz triangular wave signal into the network. And we use reservoir computing to transform that input waveform into different signals. So we've transformed it into a sine wave, square wave, a phase shifted wave, and a double frequency wave. And each one of those waveform transformations represents a different degree of difficulty, because basically, you know, you're adding certain harmonics, removing certain harmonics, and so on. And the most difficult one turns out to be converting that incident triangular wave into a double frequency wave, and that's shown in the blue dots here. Now, what this figure plots is the accuracy of doing that waveform transformation as a function of the Lyapunov exponent. And you can see that for Lyapunov exponents close to 0, where you are on this edge of chaos regime, that the most difficult task actually performs the best at lambda approximately equal to 0. For the other tasks which are less 0, there's no real advantage of being at the edge of chaos. But for a complex task, the most complex task, there does appear to be an advantage. We've also attempted some other more standard machine learning tasks. Handwritten digit classification is this example. And we've also performed a cognitive task, which machine learning doesn't do. And in that case, the cognitive task, I won't go through this because we're running out of time, but if anyone wants to know about it, I'll explain to you later on. What we were able to show with this cognitive task is we implemented a cognitive task that's used in cognitive neuroscience, and we were able to show both working memory and memory consolidation. And we found that memory consolidation was able to be achieved by imposing a reinforcement learning type of feedback on the network. And inside the network, because we did this in experiment, but with the model that we have, we're able to go in and have a look at what's happening inside the synthetic synapses. And we were able to show that with that reinforcement feedback, all the synapses that corresponded to a particular pattern that the network that we wanted the network to remember were being reinforced, and conversely, the other synapses were being punished. So it's kind of like strengthening and punishing or pruning of synapses, similar to what's been proposed in the brain. So I won't go and explain that figure there. And this is just a nice little video showing that idea of when you put in patterns, particular patterns into the network, and you want the network to remember one of them, you can then do that and either use working memory, which is a short-term memory, but if you want the network to remember over a longer period of time, you impose a reinforcement learning, which strengthens some pathways that you want the network, that are associated with the pattern you want the network to remember, and it prunes the other pathways. Okay, so three summary points. So the first one is, I hope I've demonstrated to you that these nanowire networks exhibit these sort of microcircuitry with really interesting complex structures that form as a result of self-assembly. And they have these memristive junctions. So they form what are known as, memristor networks. And as I mentioned, we're going to have another talk on that by Valentina later on this morning. And they're analogous to conductance-based synapses in biological neural networks. And this is what produces these brain-like dynamics that we've observed. I've also shown that we can perform information processing by harnessing the emergent dynamics in this reservoir computing framework. I didn't mention, but basically you read out from the network all the dynamics, and then you can use those dynamics to do linear regression or classification, depending on the task that you're interested in. Importantly, this type of learning using the dynamics, harnessing the dynamics, is what I refer to as physical learning, because you're leveraging the physics of the system that produces the dynamics, as opposed to just using data. It's not data-driven statistical learning. And the third summary was that we've also been able to show that these systems can also demonstrate higher order cognitive function, and working memory is an example of that. So my conclusion from what we've observed so far in working with these really interesting systems is that I can conclude that it's the interplay between the complex network structure, the nonlinear intrinsic dynamics, memristor dynamics, as well as the physical constraints on this physical substrate, that, to me at least so far, underpins the physical nature of intelligence in nanowire networks. And then that opens up a whole bunch of questions for other systems, and whether we can extract similar physical principles underpinning them. So thank you very much for your attention.
Yes, thank you, Zdenka. We do have time, maybe 10-15 minutes, in fact 15 minutes for questions. Yep. Carlos first.
Thank you for very interesting talk. I was wondering how much has been explored the base of also wire networks, whether I understand that the silver, but I don't know whether if you use a different method, then properties change in drug and then nothing works out, or
Absolutely. Yeah, no, that's a great question, because it is all about the material properties of the substrate. And other types of nanowires that have been used are metal oxide nanowires. And they're a little bit different. In fact, one of the ones I showed, the silver selenide ones, they're a good representation of that type of material, because the silver and the selenide are kind of integrated with each other. So you don't have a core shell structure like you do with the silver PVP. And the reason why we still observe that memristive switching there is because we don't know yet, we haven't been able to observe this with microscopy, for example, or anything. We think what's happening is that even though the material, the silver and the selenide, are integrated with each other, the silver atoms can still kind of migrate through the structure and form some kind of conductive bridge through that way as well. So metal oxides, you have to have some material that's electrically insulating, but ionically conducting. And then once you put a bias across that, it can respond.
Then could you speak to the parameters so you get more dense or dense?
Yeah, so some of the variables, I guess, in that are, for example, if you have the silver coated cases, you can imagine that if your coating was too thick, the insulating material is too thick, it might take much longer for the system to respond, because each of the individual memristors now, has much more insulating material. And in fact, if it's too thick, maybe it's the time scales are just too long. And conversely, you can go the other way. You can make shorter time scales by making that insulating layer thinner. So you have some control over the time scales of the dynamics that are being observed, at least on the memristor, the individual junction scale, that will ultimately also reflect what's happening on the network scale as well. And incidentally, for those who are interested, the typical distance between synapses, between neurons, synaptic distance, is about 20 nanometers. So we're looking at, nanoscale dimensions there as well.
Matt and then Daniel.
Thanks for the interesting talk. Early on in the talk, you explained quite clearly how the switches are connected, right? How the synapses make connections, how the switches turn on, so to speak. But I'm not sure I caught how or if the switches are turned off. I assume you had arrows on both.
Yes.
They can be turned off. What's the process?
Yes, so they do decay, and they decay by two means. So one is if the polarity is reversed, and the polarity can reverse, even if you put a positive bias across there, you can get some regions of negative polarity because you have to obey Kirchhoff's laws. And one of the laws is when you have these loops, closed loops, the voltage has to be zero everywhere. So, you've got to do the sum. So you can get that. And the other way you can do it is that in the real physical systems, and we don't have this in the model, in real physical systems, you can just get thermodynamic stochastic breakdown. So the junctions will just spontaneously decay through that. There is a third way you can also get the junctions to, I guess, breakdown. It's not so much decay, it's more breakdown. And that is that if the voltage is too high, you get a lot of dissipation, Joule heating, and that'll just, just kill that junction. But interestingly, what we've observed is that, because we have done experiments where we've ramped up the voltage, for example, what we've observed is something really interesting. We've observed that when that happens, when you get a part of the network that just blows out because the voltage going through that part of the network is just too high, the network responds and adapts. It just doesn't use that anymore, but it starts using other parts of the network. So it really exhibits this interesting adaptive behavior and resilience, what you would expect from that kind of network structure.
Just a quick follow-up. For most of the experiments that you presented, is it fair to say that the predominant process was switch connecting and not switch disconnecting, so to speak? Or am I wrong? Is there probably a
You definitely need both. I know I focused on the switching on, but there will be switching on and off. It's a continuous thing, and there'll be some parts of the network that contribute to the whole network switching on, while other parts of the networks are kind of doing their blah, blah, blah. So in the inactive phase, let's say you're below the threshold, there'll be a lot of on-off switching, and those are really interesting fluctuations. There's definitely input signal going in, but it's below a threshold. So there's a lot of on-off switching just going on all throughout the network. And then when you increase to going above the threshold, then there'll be a portion of the network that then activates, but the other part of the network will just still stay switching on and switching off.
Daniel?
One of the earliest, probably most famous neuromorphic architectures is, of course, Gordon Hask's. I'm not sure if you're aware of that.
No, I'm not.
I felt this really, he would have really liked to have materials you have. He had built this device which would actually distinguish different sensoric signals, actually hear two sounds. And it was basically grown filaments of some substance. I forgot exactly how it's done. There's no theory to that. Now, you were talking about computation. Now, computation is something we can do. We know how to do reliably. We can design it. I do think that a much more, in the sense of much more useful application of this would be sensing. Because sensors are cheap in nature, right? Nature and many problems that an organism has is solved by sensors rather than computation. So my question is, what's the perspective of that?
You are absolutely right. And of course, sensing is, you have this continual stream of dynamical information, and that is ideal for these systems. And you're absolutely right. Computing is not really what this should be for. We've ticked off a whole bunch of machine learning benchmark tasks because you kind of need to do that to tell people that you're doing something interesting. But you are absolutely right. The sensing, it's true. The sensing application is the killer app, if you like. Yeah.
Georg and then Simon.
We have one online as well. Yeah.
I'll check that. Thank you.
Think about that in the beginning. Anyway, so really interesting stuff. I'm not sure I understand everything correctly. So is it correct to say that the network themselves, they are essentially not, they are static in their structure, right? So,
Yes.
so they form and then
Correct.
they are there, right?
Yeah.
So there's no adaptation on that.
No, it's only the electrical signals that are.
And so, I mean, in the brain, when we speak about this criticality, we speak about self-organized criticality because the network itself regulates to the place where it becomes critical or close to critical, subcritical, whatever. And otherwise, as you said, in the hiding model, I have to tune the hyperparameter to the critical value very precisely.
Yeah.
And so I'm wondering, what is that tuning in your case, and how did you manage to get that thing critical?
Yeah, great. There's a lot to unpack in your question.
Yeah. So
You know, probably the most important one being self-organized criticality. We haven't gone there. You know, self-organized criticality is a difficult beast to get into. I guess, you know, we have a control parameter, the voltage, and we observe a threshold for that. So that's kind of analogous to the icing model. But on the other hand, you know, we can't just look at the simple icing model either. We've got to think of something like icing model under an external magnetic field or something like that as well. So it's no longer just temperature. You know, we have that external field. But one thing I will say about about what you've mentioned here is that, you know, one of the reasons why self-organized criticality was initially proposed is because the mean field theory for a system like this one and, you know, other many body systems breaks down when you have, you know, criticality phase transitions. So there's no way you can really explain it. And so self-organized criticality was kind of thought to provide a way in which to describe a system in that critical state. I don't know if we have that here in our system. I don't know if people are still proposing that it exists in the brain, for example. But certainly we have started looking at a mean field approach to describe our system. So maybe I'll get back to you in 2 years.
Simon?
Got a feeling that I may, as a result of the last question, fundamentally misunderstood the way the system works. Well, I'll go anyway. So I'm thinking, I see a network. I'm imagining that you can switch it on or off as by applying voltage or particular connections, switched on or off by applying voltage. What I'm imagining is that a driver for that is a change in the material properties of that connection, where it either it's broken or it's made, and then that gets me going. I think, well, how reversible? I get that you can have the system changes state as a result of exposure to the voltage, so you can get some of this set connection switched on or switched off, or, you know, combination of the two. What I don't understand is, as the process continues, do you find that the system remains, I suppose, responsive to learning? So you can have things, connections switched off at one stage and then switch on again at
Yes.
another. And do you find you get fatigue setting in as a result of this?
Yeah, no, great question. So that's a great question. So if you imagine what's happening at all those individual junctions, this is this little filament forming, right? And let's just say, you know, because the voltage is continuously redistributing itself, so the bias is changing everywhere across those junctions.
Yeah.
So let's just say this, you know, some junctions are experiencing a reverse bias or just a lower voltage.
Yeah.
So, you know, the filament can't form anymore, or it starts to decay, but it doesn't completely decay. It has some memory because there's still a little bit of filament left from the previous, you know, period of time. And so when it receives another, so the signal's continuously coming in. So when it receives a signal that's similar to the previous signal that caused the formation of that filament in the first place, it'll remember that. So the memory that we observed in the hysteresis curve is actually caused by the little filaments not completely decaying. It takes time for them to decay. And conversely, if the signal comes back before it's completely decayed, the junction will remember that signal.
Okay. So one last question, Brett, and then we'll break.
Yeah, you talked about learning, and I'm trying to understand a little bit what the process of learning about reinforcement learning. So that I mean the big learner at the moment is good old back propagation, which even though the person who has pushed this and like a lot of deep learning stuff thinks that we must one day discover back propagation in the brain because clearly it's the best way of doing everything. Seems pretty doubtful at this stage of back propagation. So is there anything, what's the learning mechanism most like in yours? Is it more like Hebbian learning? Is it pure reinforcement where there's an external actor on it? I'm just trying to understand a bit of what.
It is more Hebbian, and in the reservoir computing framework, I just put reinforcement learning aside for a minute. In the reservoir computing framework, all the learning is done in an outside layer. So nothing, the network is not touched at all. It just evolves. And then you have an external linear layer where you just do your learning using, very, very computationally efficient algorithms. Yeah.
So there's no remodeling of the actual learning.
No, so we don't need backprop or anything like that. We just let it do its thing and we just read out the dynamics and then we use those dynamics in an external layer. Yeah. Yeah, but when I mentioned reinforcement learning, that was a different setup. That wasn't reservoir computing. In that we are using the network and so there we've got multiple input electrodes and multiple output electrodes, and we control the voltage levels on the output electrodes to manipulate the pathways that we want to reinforce. And this goes back to my answer to the previous question, that those pathways that we want to reinforce, we want the network to remember those pathways. So we don't want that filament to completely decay along those pathways. So we do that with that kind of like reinforcement learning. We're providing external feedback back into the network. I wouldn't call it backdrop. We're not, I wouldn't call it backdrop because it's a completely different paradigm from the machine learning neural network approach.